Hi everyone, welcome to this video on the vertical motion lesson, lesson 15 in the forces and space scheme of work. You may take a look at this lesson and think it looks a little bit weird, a little bit unusual. It's not the kind of thing that I usually see addressed, certainly at Key Stage 3 and often not at Key Stage 4. The reason it's in here is because as an A-level physics teacher, I remember doing some of the kind of problems that we do at A-level physics, and students just seem really baffled by this idea that when things are going up and down at the very top, and sometimes at the very bottom, but certainly when they kind of go up and reach the very top of their motion, for an instant they are stationary. And this seemed to just blow students' minds. And actually, I realised that they didn't have a really clear picture of what was going on in these kind of problems that we're going to look at today. Bullets being fired vertically upwards, or people jumping up and down on trampolines and so on. And that's why they found those problems really, really difficult. So what I wanted to do is just get students thinking, again, really, really hard in terms of the concepts that we've been looking at, Newton's first and second law. It's not, there's no kind of extra skills required to be able to access this lesson. It's just another way of getting them thinking in terms of those concepts, which, again, the hope means those concepts will be really, really secure. They'll be in the habit of thinking like that by the time they get to Key Stage 4. So I'm just going to go through one example here. The way this lesson is structured is that the teacher draws one example, then there's some whiteboard questions checking whether students are able to tell you, as a teacher, what direction the velocity acts in and what direction the acceleration acts in at various points. And then there's a couple more examples that they've got to draw diagrams for and identify the direction of velocity and acceleration. So it's quite a simple lesson, but conceptually it really requires some thinking. So the example that we're going to model is a person, for whatever reason, firing a bullet from a gun. So what we want to do is consider the forces acting on this bullet and the direction of velocity and acceleration of this bullet at various points. So let's start with the bullet just here, just after it's been fired out of the gun. If you want to kind of draw something like that to show that it's moving really, really fast at that point, that would help. Because that's the first thing that we need students to recognise, is that at that instant, just after it's been fired, the bullet has a very high velocity upwards. Now, we're going to take upwards as positive because that's the way the bullet starts. Again, it's fairly arbitrary, you can do it either way, but I think that's more intuitive to students in year 8. So let's just start by saying, okay, we're going to call everything that's moving upwards as positive. So again, using that idea of kind of vectors and plus and minus to represent direction, because that's really, really important. And what we can do here is say, well, at this stage, here, the bullet is moving really, really fast. It's going in that direction, so its velocity is upwards like this. So I'll put a red arrow and a V like that. Now, next I might think, okay, let's draw the forces. Now, we're going to ignore drag force, and it's worth saying to students why we do that. Really, it's to simplify the problem, and physicists do that all the time. They make assumptions that just effectively make the calculations easier. So for this example, we're just going to ignore the drag force. But if students say, oh, but isn't there a drag force acting? Well, yes, there would be, but we can kind of ignore it, and it gives us a pretty good description of the motion. Not perfect, but good enough for what we want today. So actually, the only force acting here is the weight. I'm going to draw the weight acting down. Now, a bullet would actually have a very low weight, wouldn't it? But I've drawn quite a long arrow anyway. So we've got the weight acting down like that. And what you want students to recognise is that there's nothing else acting on the bullet. And here you can maybe already see we're kind of foreshadowing the lesson on projectiles and coming back to that idea we saw right at the start of this scheme of work when we looked at the basketball going through the sky. And actually, if you've got an object in midair, the only force that's acting on it is that force of gravity from the Earth pulling it back down. And Hopefully, therefore, what they will recognise is, well, if the only force is the weight acting downwards, then that must be the direction of the resultant force. There must be a resultant force acting downwards. And therefore, even though the velocity is in that direction, our acceleration, which I'm going to draw with 2 arrows to show how it's different, is acting downwards like that. So this is our first picture just after the bullet has been fired out of the gun. We've got a very large velocity in that direction, but we've got an acceleration in the opposite direction. And what you want students to recognise here, if we move the picture up, I'm going to kind of move temporally across the page here. So let's draw the person again. So this is a little bit later. Now, I'll draw their gun as well. Now the bullet is getting pretty high up. And what you want them to recognise is that, firstly, the force that's acting is still just the weight. That. But if the acceleration, if you've had this negative acceleration in the opposite direction to motion, what you want them to recognise is that as it gets close to the top of its trajectory, actually that velocity is going to be a lot smaller. It's slowed down because gravity is decelerating it. So the velocity is still upwards, it's still positive, but it's a lot smaller. But because the weight is still acting downwards and no other force is acting, we've still got this same velocity acting downwards like this. And again, you might want to just remind students, because this is going to come up in the later questions, that we could call that a negative acceleration. So we've still got this negative downwards acceleration, even though the velocity is still upwards and positive. Now, again, this might take a bit of questioning. You could get students to think, okay, if the bullet goes upwards and it decreases in speed because it's accelerating backwards or it's decelerating, and then it keeps going upwards and its speed is less, and then it keeps going upwards and its speed is going to get less, at some point, something's going to happen to the velocity. What you want them to recognise is, at its highest point, just for an instant, so I'm going to draw my person here to kind of show the scale of this. So here's the bullet up here. At a certain point, that velocity is actually going to go to 0. And that's the very highest point that the bullet reaches. Just for an instant, we can imagine the velocity is stationary. It sort of gets to the top, slows down, slows down, slows down, and then is still. And as you can probably guess, it's then going to start speeding up in the other direction. But what we want to emphasize to students is at the highest point of any journey, the velocity is 0. Now, this, again, doing a bit of foreshadowing here, another way of thinking about this is in terms of energy. So another way physicists could solve this problem is to say, well, we started with lots of kinetic energy down here, or down here when the speed was very low, but then we ended up with lots of gravitational potential energy. All of that had been transferred up here, and that's a mechanical transfer. That's another way of thinking about it. Now, again, what we want to do is just model this really disciplined thinking and say, but let's consider the forces. Well, there's still only one force acting. It's still that force of weight acting downwards, gravitational pull of the Earth, and so on. And therefore, if we think about the acceleration, it's still exactly the same. It's still this one acting downwards like this. And what we hope they're going to recognise, this is what we call uniform acceleration. Some of those equations that we start to look at GCSE, like v squared equals u squared plus 2as, we look at as the SUVAT equations at Key Stage 5, they're all here, okay? And if we give them this picture, then they've got a much better chance of understanding that. So then we think, okay, it's stopped here. Is it just going to stay stopped? Of course it's not. It's accelerating that way. So if it's accelerating that way, that means it's getting faster in this downwards direction. So what it's going to start doing, if we draw another little person over here, just to show the scale, what it's going to start doing is moving back downwards. So at this point in the journey, it's now started moving downwards like this. And notice where it had a positive velocity in the beginning, now it's got a negative velocity because it's accelerating in the negative direction. Why is it accelerating in the negative direction? Well, if we draw the force diagram, still just the weight acting. There's no other forces affecting it. We're ignoring the drag just to make things a bit simpler. And therefore, it must still be accelerating in that direction because there's a resultant force downwards like that. And then we can draw our last one our last diagram, maybe when the bullet is about to hit the ground. Hopefully it's not going to hit the person. That'd be a good question to ask students, actually, because if we ignore the air resistance, then the bullet should hit the person at the same velocity with which it left the gun. So it would be like being shot at point blank range. So clearly that's not something we want to happen. So let's imagine the bullet is going to fortunately miss that person, and it's going to land down here somewhere. Let me just move. Yeah, it's going to land down here. Now at this point, again, what we want to elicit, well, it's been accelerating all the way down here in the negative direction. So now it's going to have quite a large velocity again. So I'm going to draw a velocity like this. But again, what force is acting just before it hits the ground? Well, it's still just the weight of the Earth. Weight of the Earth, I beg your pardon. The weight of the bullet caused by gravitational attraction of the Earth. And therefore, it's still accelerating downwards like this. Just as it has been all the way through. And that's what we want students to notice, is that what seems kind of complicated when we consider it in terms of the velocity, we've got this continually changing velocity, starts high, gets lower, goes to 0, gets higher in the opposite direction, gets very high in the opposite direction. The acceleration here, and that's because of the forces that are going on, the acceleration is constant. It's a constant negative acceleration. And if students can grasp that, that's a really, really profound and powerful way of understanding what's going on in these sorts of scenarios. And when they get to Key Stage 4 and Key Stage 5, it's this kind of understanding that's going to allow them to solve some of those more difficult problems. So hopefully that's clear. In the next video, we will be looking at stopping distances.